Hello and welcome. This is the course on stochastic process and theory of queues. In this lecture, we will start with a new topic. We will be giving a brief introduction to the so-called renewal theory. We will see in this lecture what renewal processes are and how it is more general than the Poisson stochastic process, and it can be used for modeling a wide variety of systems that we encounter in science and engineering. So let us consider a stochastic process which has a discrete state space but continuous parameter or time. Let us denote it as n of t for t greater than 0. And in particular, we will consider the process such that n of t represents physically the account of some discrete quantities or discrete events that take place. For example, n of t may represent the number of births that take place in a country, number of accidents that has occurred, number of time let us say the stock market price has crossed a threshold during a trading session, and things of that kind. Basically, it is a count of some event that is of significance to the current discussion that we are interested in. So because it physically represents a count, we will call it as a counting process. But when we want to model such process, counting process, we expect n of t to have some properties. First, n of t represents a count, means some discrete entities or events. So n of t has to be an integer. Further, we demand that n of t has to be a non-negative integer because it represents a physical quantity that has occurred, discrete lumped quantities that have arrived or that we have counted still at time. It cannot be negative, so it can only be positive or 0 in this special case. Further, as time progresses, if you look at the way the n of t changes, n of t represents a monotone non-decreasing function of time. Okay, so that is for a counting process. If n of t represents a discrete state continuous time process, then it might look something like what is shown in the figure. So this is true not for a counting process, this is wrong. It is true for a discrete state continuous time process because the number can increase or decrease, but it can take only finite integral values, which is non-negative integral values. This may be a number of customers in a supermarket at a given time and so on. So it can increase or it can decrease and so on, but always taking some integral values. The time at which it can change is arbitrary time. So on a continuous range, time can be it can be monitored at any given time t. So t is the parameter is as a continuous range. So this is for a discrete state continuous time stochastic process. But if it has to represent a counting process, it cannot decrease. It has to be a monotone non-decreasing function. Then without loss of generality, we can take n of 0 equal to 0. That is, at an arbitrary time 0, we take the number of counts is 0. If you assume that the number of count has some value at an arbitrary time, we can always discard that count and take it to be start counting from that time onwards. Therefore, there is no loss of generality by taking n of 0 equal to 0. Further, the monotone non-decreasing nature of n of t demands that for two time points t and s, where t is less than or equal to s, n of s minus n of t, this quantity is again has to be non-negative, and this signifies the number of events that has occurred in the interval t comma s, where this is a semi-open interval. Here t is not included but s is included, because n of t represents the number of events that has taken place from 0 up to t, which includes t. So here if you decrease, if you find out n of s minus n of t, t has to be removed but s is included. Well, now we can see that this is a counting process. We have already looked at one such counting process, which is the Poisson stochastic process. Poisson stochastic process has in addition the condition that it has independent increments. That is, the number of events that has occurred in non-overlapping time intervals are independent. To be precise, if t1, t2, t3, t4 are successive time points, in the sense that t1 is less than or equal to t2, less than or equal to t3, less than or equal to t4, then n of t4 minus n of t3 and n of t2 minus n of t1 are independent of each other. The number of events that occur in the interval t3 to t4 is independent of the number of events that has occurred between t1 to t2. So the Poisson process in addition has certain Poisson PM of prescription, which will also make the process such that the time duration between successive arrivals or events that occur are independent of each other and have an identical distribution, and that distribution is the exponential distribution. So if you look at the time interval between successive events, they are random variables. We can construct a stochastic process as a sequence of random variables which all represents the time interval between successive events of a counting process. So x1, x2, x3 is an indexed family of random variables, or we can construct xi, I is equal to 1, 2, 3 and so on. Whereas these random variables are continuous valued random variables, and we index them using a discrete index. So it is a continuous state, discrete time, random stochastic process. Which one? xi, I is equal to 1, 2, 3. So if you look at that xi's, they are all independent of each other. x1 and x2, x3 are all independent. Further, for the case of the Poisson process, they have identical distribution. And last but not the least, that distribution is the exponential distribution. So xi's are IID exponentially distributed random variable. That makes the Poisson process to be a Markov process. Why? Because one, there is an independent increment nature of the Poisson process. Second, the event duration, time duration between successive events, or xi is exponential, which also has the memoryless property. So if you observe the process as an arbitrary time, the number of events that has occurred before that and the future number of events that will occur in a future interval are independent. In addition, the remaining time it takes for the next event to occur also does not matter at what time point you observe the process. That simply follows from the exponential nature of the interarrival time. Therefore, Poisson process is a Markov process. We will make it little bit more mathematical, this statement. Given 3 time points t3, t2, t1, such that t3 is greater than t2, which in turn is greater than t1, the Markovian property of a Markov stochastic process demands that probability that n of t3 equal to n3, given that n of t2 equal to n2 and n of t1 equal to n1, is simply probability that n of t3 equal to n3 given n of t2 equal to n2. That is, given the past, that is the information, that is n1 being the number of events that has taken place at the n1 is the value of n at the time t1, and the present, that is n2 at the time t2, the future statistics, namely n of t3 equal to n3, is independent of the past given the present, because t2 is more recent than t1. Given t2, t1 is irrelevant for predicting t3. That is what we mean by this statement. To prove it, we can write this left hand side, which is n of t3 equal to n3 given n of t2 equal to n2, n of t1 equal to n1 as follows. This is like a probability of A given B. It can be written as probability of A intersection B by probability of B. That is n of t3 equal to n3, comma, n of t2 equal to n2, comma, n of t1 equal to n1, divided by probability of n of t2 equal to n2, n of t1 equal to n1. Now, let us multiply let us look at this one, the numerator of this expression. This condition can be written alternatively in this manner. That is, n of t1 equal to n1 is written here. And look at this one, n of t2 equal to n2, comma, n of t1 equal to n1 means in an interval t2 minus t1, there has to be n2 minus n1 events. That is, n of t2 minus n of t1 equal to n2 minus n1. That is what these two together indicate. Similarly, if you look at these two together, it means n of t3 minus n of t2 equal to n3 minus n2. So the numerator of this expression can be written in this manner. So for the numerator, we can plug in the Poisson PMF expressions. What it means is probability that n of t, and you will look at these things. 0 to t1 is an interval which is independent of t2 to t1 to t2, which is independent of t2 to t3. Now let us invoke the independent increment nature of Poisson process. So these are three events which are independent of each other. So probability of the intersection of three events A, B, C, that is probability of A intersection B intersection C, is probability of A into probability of B into probability of C. So we can multiply these probabilities. That is probability of n1, n of t1 equal to n1 multiplied by probability of n of t2 minus n of t1 is equal to n2 minus n1 multiplied by probability that n of t3 minus n of t2 equal to n3 minus n2. We can write it like that and then substitute the value for these expression. Probability that n of t1 equal to n1 is nothing but e power of minus lambda t1 power n1 by n1 factorial. Similarly, if you look at this, the probability of this event is e power of minus lambda t2 minus t1 into lambda t2 minus t1 power n2 minus n1 by n2 minus n1 factorial. And for the last one, it is e power of minus lambda into t3 minus t2 into lambda into t3 minus t2 power n3 minus n2 by n3 minus n2 factorial. Now let us look at the denominator, which is this. probability that n of t2 equal to n2 and n of t1 equal to n1 is again that in 0 to t1 there has to be n1 events, and between t2 to t1 there has to be n2 minus n1 events. The corresponding expression is e power of minus lambda t1 into lambda t1 power n1 by n1 factorial for the number of events in 0 to t1 to be equal to n1. For the next one, it is e power of minus lambda into t2 minus t1, lambda t2 minus t1 power n2 minus n1 by n2 minus n1 factorial. So this is the numerator, this is the denominator. If we divide, then we can see that this is simply equal to e power of minus lambda. The only thing that will survive is this e power of minus lambda t3 minus t2 into lambda t3 minus t2 power n3 minus n2 by n3 minus n2 factorial, which is again nothing but this conditional probability, that is n of t3 equal to n3 given n of t2 equal to n2. Therefore, we will see that the Markovian property has been obeyed by the Poisson stochastic process. So basically, the Markovian property is obeyed because the time duration between successive events are exponentially distributed. If it were some other distribution, then this property, Markov property, would not be obeyed. So the exponential distribution is the one which brings in the memoryless property, and therefore the stochastic process becomes a Markov process. To give an example, let us say we have got a stack of or a box of light bulbs, all manufactured using a similar manufacturing process, and therefore you expect their lifetime of these components to be identical, and because they are random variable, they have an identical distribution. Further, they will be independent because one light bulb is not going to influence the lifetime of other light bulb. Let us assume a case where we put one bulb randomly picked from that lot into use and use it. Whenever the bulb fails, we immediately replace it by another bulb from the lot and keep doing it like this one. So by event here we mean the failure of a bulb. Okay, so events will occur one after another at random time points. To begin with, at the time 0, with the first bulb starts is being put into use. Let capital T1 be the time at which it fails. So the lifetime of the first bulb is x1. Bulb 2 is being put into use at the time t1 and it works till t2. So t2 minus t1 is what we call as x2. Similarly, t3 minus t2 represents the lifetime of the bulb 3, which is x3, and so on. So x1, x2, x3, x4 are all the lifetimes of the successive bulbs. They are all identically distributed, independent of each other. If we further assume they are exponentially distributed, then the number of bulbs that you would have used till time t is a Poisson stochastic process, because it is a count of the number of bulbs that we have put into use till a given time t, and the duration between two replacements is the lifetime of a bulb which has exponential distribution. Therefore, n of t, that is the number of bulbs that we have used so far, is a Poisson stochastic process. So here what happens here is, at a time t, when we know that 5 bulbs have been used, okay, have been used and then replaced, and a 6th bulb is in use. So which means that the time t is such that it is more than the sum of the lifetime of bulbs 1 to 5. x1 plus x2 plus x3 plus x4 plus x5 is less than that time. Then only 5 bulbs have been replaced. then the sixth one is under use, which means that x1 all the way up to x6 is greater than t. That is why sixth bulb is still in use. So the time at which we say that 5 bulbs have been used so far, have failed so far, is a case where the t is such that the sum of x1 to x5 is less than t, x1 plus x6 is greater than t. So if you now ask a question at some other time, yes, what is the probability that 10 bulbs would have been replaced? For that to occur, we should look at the time interval s and t, find out s minus t, what is the probability that certain number of bulbs would have been replaced and so on. But the thing is, at the time t, the sixth bulb is under usage, and we have to look at the residual lifetime of the sixth bulb to find out when sixth replacement will occur. And after that, we know on the average x bar, if that is the mean of that exponential IID random variables, that will be the expected lifetime of every other bulb. But here the residual lifetime of the bulb under usage is very important in order to predict the number of replacement that would have occurred at a future time. But it so happens for the exponential random variable, the residual lifetime of a component having exponential lifetime distribution is still exponential with the same parameter. That is what makes the process to forget history, and only thing that we have to remember is the value of the process at the time t. That is the number of replacements or renewals, which we will call it later, as that has occurred till a time t. Therefore, Poisson process becomes a Markov process. But in general, if you look at the lifetime of a component or the time duration between two events and so on in a counting process, as we can envisage, it will be encountered in many phenomena in our walks of life. But it may not always be valid to assume that the time duration between successive events are exponentially distributed. They may have a general distribution, but it may still be valid to assume that the time duration between two events are independent of each other. For example, if you look at the arrival of some taxis in a taxi stand and so on, or the customers to a marketplace and so on, the duration between arrival of two customers need not always be exponentially distributed, but it is quite valid to assume they are independent of each other. They have independent distribution. So now we will generalize and take a case where the inter-arrival time between successive customers or events and so on are not exponentially distributed, but have a very general distribution. So we have got x1, x2, x3 and so on, or the duration between successive events that has occurred, and the number of events that has occurred till a time t is still a counting process. It has to be still non-negative, and it has to be monotone, non-decreasing. All these are still valid, but only thing is xi's are all IID, but not necessarily exponentially distributed. If they are general distribution, what will be the implication? Then, if you look at an arbitrary time and then observe the number of events that has occurred, then what will happen is, if let us say take the same case of the light bulbs lifetime, now they are not exponentially distributed, but they have general distribution. If you assume that, if you find that at the end of a 7th month, 3 bulbs have been replaced, and if you ask what is the probability that in 1 year 6 bulbs would have been replaced, then at the end of the 7th month, while the 4th bulb in use, we should know when this fourth bulb is likely to go off, so that the fifth one will come, and how long fifth one will work, and then sixth one will also should be replaced within a year, but not the seventh one. So that is the case wherein the number of replacement in 1 year will be 6. For that we should know the residual lifetime of the remaining, the bulb in use. But now if it has a general distribution, the residual lifetime cannot be easily characterized. That depends upon the time of observation of the process. So the history helps in predicting the future, and therefore it is non-Markovian. However, if you look at a time at which a bulb is just replaced, at that point of time, let us say at a time t when 5 bulbs have been replaced, next, and then a new bulb is just put into use. At these points, it is enough if you know the value of the process as 5. Okay? When it was having the value of 4, 3, 2 will be irrelevant, because the new bulb that is being put into use as a general distribution, whose characteristics will know, statistical characterization as the mean or the expected duration of the lifetimes are all known, and further on every other a random variable that comes in that sequence of stochastic process have the same distribution, they are independent and so on. So future statistics can be predicted given the present. This occurs only at some special points when events occur, in this case when the bulbs are replaced. So these are the points at which history can be forgotten and present information is enough for predicting the future. So the process behaves like a Markov process, or we say that the process renews itself. It statistically becomes as if it were the one which is at the beginning of the observation at t is equal to 0. So we say that these processes at this point, the process renews itself and statistically becomes as if the way it is at the beginning of observation. So those points are called as the renewal points, and these processes are called as the renewal processes. And so renewal processes are the one which are counting processes with independent increments, but only thing is the time duration between successive events that occur or has a general distribution. So in other words, a renewal process having an IID random, exponentially distributed random variable as the inter event duration time is a special case, and it becomes a Poisson process. The point at which the events occur are called as the renewal points, and the process statistically renews itself and behaves like a Markov process at these points, not at any arbitrary points. And each time an event occurs, we say a renewal has occurred. And because of this nature of this counting process, we can characterize the renewal process and arrive at certain characterization, but it will not be as amenable as a Markov process, but still statistical characterization is possible because of this IID nature of the exercise, and we will do those characterization in the next lecture. Thank you.